Hello everyone, welcome to the Tim Booker channel. Wishing you an enjoyable time listening to books. Today, the book I'll interpret for you is, Your Brain is a Time Machine. When you hear the term, time machine, what's the first thing that comes to mind? Is it any of the doors from the Doraemon animation? Is it time travel from a sci-fi movie? Or perhaps time leaps from a TV series? The idea of a time machine represents humanity's dream of breaking barriers in space and time, yet it remains a fantasy for now. However, this book tells us differently. It suggests that the brain is a time machine, a mechanism for perceiving time, capable of transporting you to the past or the future. The author of this book, Dean Bunamano, is a professor of neuroscience and psychology at the University of California, Los Angeles. He has conducted extensive research in neuroscience and frequently conducts lectures and interviews on the subject. Today, the book I'm interpreting for you is Professor Dean's exploration of time from the perspective of neuroscience, a popular science work. So, let's follow the author's rhythm and embark on a mental journey through time. Let's delve into the time stories unfolding within the brain. This journey will revolve around three questions. Firstly, how does the brain perceive time? Secondly, understanding the illusions in how the brain perceives time. Lastly, why do we say the brain is a time machine? Before delving into how the brain perceives time, let's discuss the concept of time itself. The term time is familiar to everyone, so much so that we rarely ponder what time actually is. For millennia, philosophers and scientists have contemplated the mysteries of time, leading to two fundamentally opposing views. The first understanding is that time is a unidirectional flow, irreversible and ephemeral. The past is gone, the future uncertain, leaving only the present moment as truth. The ancient Greek philosopher Heraclitus expressed this with his famous statement, "You cannot step into the same river twice." Confucius also reflected this view, stating, "The past cannot be changed, the future is yet in your power." This concept aligns with our subjective perception, as we can distinctly feel the passage of time. We exist in the present. However, physicists hold a different understanding of time. In both classical Newtonian physics and modern relativistic and quantum physics, time is reversible within the laws of physics. In other words, the direction of time holds no significance in physical laws. If one were to write equations describing the moon orbiting the Earth or the Earth orbiting the Sun, these equations would remain equally valid whether time moved forward or backward. Physics doesn't ascribe any special significance to the present or now. Within its equations, past, present, and future coexist as equally real. They're akin to points displayed in different locations in space. This forms the backdrop of a space-time universe composed of three spatial dimensions and one temporal dimension. As Einstein famously remarked, for those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. However, this understanding of time contradicts our intuition. We perceive the flow of time distinctly. Could our perception of time's passage truly be a persistently stubborn illusion? To unravel this mystery, we arrive at the first question posed by the author: how does the brain perceive time? Here, we encounter two systems, the biological clock and synaptic connections among neurons, both serving different time scales. The biological clock is involved in gauging longer time spans. Scientists conducted an experiment involving mice housed in an alternating light-dark room, mimicking day and night. Despite eliminating external clues of day and night, the mice displayed robust rhythmic activities, transitioning between periods of activity and rest. This indicates the presence of an internal clock within animal bodies regulating daily life, synchronizing with the Earth's day-night cycle. But how does this biological clock manifest within humans? Our bodies receive information from sensory organs interacting with the external world, transmitting this data to specific brain regions, shaping auditory, visual, olfactory, gustatory, and tactile senses. However, humans lack dedicated organs to directly sense or detect time. The brain also lacks specialized regions solely dedicated to time perception. The author reveals that the ability to perceive and judge time is inherent within our brains and embedded within our bodily organs and cells. Essentially, the human body houses internal clocks distributed throughout, with each cell containing a 24-hour rhythm associated with gene expression. Gene expression governs the transmission of genetic information within cells, guiding the synthesis of proteins. Due to the rhythmic nature of gene expression, cells possess their own rhythms. Cells maintain periodic activities through automatic regulation and feedback mechanisms, forming the intrinsic cellular chronometers within the human body. Instructions for the periodic activities of cells originate from the brain's bottom region called the suprachiasmatic nucleus, SCN, receiving light information from the eyes and relaying hormones to the body's cells, informing the body about the current day or night, regulating wakefulness, sleep cycles, jet lag from international travel, and disruptions caused by continuous overtime, night shifts, and staying awake. These disturbances not only induce brain fatigue but also disrupt cellular rhythms, affecting overall health. The biological clock's timekeeping in the body operates on scales of days and hours, which are not suitable for comprehending language or discerning shorter intervals like music beats. For perceiving shorter durations, we must turn to neurons in the brain. Principally, any regularly changing and reproducible physical phenomenon can be used for timing purposes. For instance, conventional timepieces or pendulum clocks operate based on regular movements. In fact, the body also uses a similar principle to judge time, through rhythmic oscillations. But what exactly constitutes these oscillations? Our brain comprises nearly 100 billion neurons connected through structures called synapses, enabling communication between neurons. These connections form an extensive communication network, resembling passing a ball between teammates in a football game. These neuron connections possess specific directions and plasticity, crucial for timing. What is plasticity? When neurons transmit signals between each other, differing time intervals between signals result in varying synaptic strengths, consequently generating different electrical signals. Hence, synaptic strength encapsulates temporal information. Therefore, neurons can discern different time intervals, termed synaptic plasticity. Certainly, this is just a simplified explanation of the brain's time judgment mechanism. The actual situation is much more complex. A cubic millimeter of the brain's cortex contains hundreds of thousands of neurons and billions of synapses. To explain how the brain's cortex processes time, the author proposes a model called the state-dependent network. Regarding state, let's draw an analogy. Imagine several billiard balls on a table, each in different positions and motions. The state of the billiard system is defined by the position and motion of each ball. Theoretically, knowing the state of the billiards at a certain moment allows us to understand its state at some past or future moment. Similarly, for neural networks, at a specific moment, which neurons are generating signals and the synaptic plasticity of these neurons reflect the current state of the brain system. Thus, we can use the brain system state changes to judge changes in time. It's essential to note a difference between the brain and man-made clocks. Mechanical clocks, apart from regular pendulum or crystal movements, require additional gears or digital circuits to count each oscillation. Herein lies the distinction. While judging time, the brain doesn't operate with separate systems for each clock. Instead, it harbors a singular system within its neural loops. Every part of the neuron contributes instantaneously. Contrarily, the brain doesn't have a single clock at work, multiple clocks operate simultaneously. Consider it akin to cooking 3 different dishes in the kitchen simultaneously. The brain uses 3 devices that require different alarm settings. One strategy involves setting one clock for 3 tasks, while the other employs 3 separate clocks for each task. Clearly, the second strategy holds an advantage. When one alarm sounds, you know which task to attend to immediately, ensuring a smooth completion of all 3 tasks. Summing up the first query, the brain relies on synaptic plasticity among neurons to judge and record time. Neurons can selectively respond to different time scales, allowing the brain's multiple clocks to accomplish and coordinate various time tasks. Therefore, the brain acts as a sophisticated machine for time judgment, utilizing multiple clocks for specific tasks at particular moments. This intricate mechanism not only operates in real time but also generates various sensations. We've all experienced the perception that time never returns, but is this perception merely a brain illusion? Illusion, in this context, doesn't signify an erroneous perception but rather a construct of the mind, not faithfully representing external physical phenomena. Therefore, let's explore the second question: how does the brain perceive the illusion of time? Einstein famously quipped in his theory of relativity that an hour with a beautiful girl seems like a minute, but a minute on a hot stove feels like an hour. Clearly, the same duration in different environments or mental states results in distinct time perceptions. Subjective perception of time changes under varying emotional stimuli. In moments of danger or tension, the brain enters slow motion mode, while in joyous or pleasant emotions, time feels fleeting. In the 19th century, scientists interviewed individuals who had experienced extreme falls, accidents, or near-death encounters. 95% reported heightened reflexes during those brief moments, but the events seemed to unfold in slow motion. People who experienced highly emotional events, like watching horror movies or engaging in skydiving, often overestimated the duration of these events. Conversely, during enjoyable activities like reading a favorite book or engrossing in a TV series, time seems to fly by. One classic example illustrating time perception is the holiday paradox. While waiting for 5 hours due to a delayed flight en route to a vacation spot, it seems interminable. But during an exciting day exploring the destination, time appears to pass swiftly. Remarkably, a week later, the flight delay is a negligible memory, while the busy day at the holiday destination seems considerably longer. Waiting at the airport involves forward timing, experiencing the passage of time, relying on the brain's timing circuits. However, recollection engages backward timing, mostly reconstructing events stored in memory to assess the pace of time's passage. These experiences demonstrate that in many situations, our perception of time becomes distorted. The human brain has the ability to compress or expand time, a feature employed daily. For instance, we unconsciously adjust speaking speed when talking to babies, elongating the time taken. Similarly, in lectures, when time is running short, speakers speed up, shortening the duration. The capacity to perform the same action at different speeds is a fundamental characteristic of the human brain system. Time perception isn't only influenced by background contexts and emotional states, it's also affected by spatial perception. Swiss psychologist Piaget conducted experiments with children observing two snail toys of different colors moving along parallel lines, starting and stopping at the same time from the same position. The blue snail moved faster and traveled further. However, even after witnessing the entire process, children still incorrectly believed that the snail traveling further stopped later. Many of Piaget's experiments concluded that only when children understood the concepts of space and speed could they gradually comprehend time. Further theories suggest that humans primarily conceptualize time through space. Our ability to comprehend the concept of time amplifies through neural circuits for navigation and spatial understanding. For the brain, space is an easier domain to understand. Reflect on the language used in daily life to describe time, often associated with spatial concepts. For instance, phrases like short-term and long-term. The relationship between space and time is deeper than just language, it's an essential aspect of human perception. The author referenced a study where identical time intervals elapsed sequentially as 3 dots flashed on a computer screen in left, middle, and right positions. Participants were asked whether the time interval between the first and second dots was longer than that between the second and third. Now we come to the third question, which is also addressed in this book: why is the brain considered a time machine? This is because the brain not only perceives time but also retains the past, predicts the future, and navigates on a mental timeline. This functionality is akin to the shuttle function of a time machine. Psychologists refer to this ability as mental time travel. Engaging in mental time travel is a crucial and unique cognitive ability of humans. It's due to this ability that humans understand planting seeds in spring to counter potential winter hunger and building shelters to withstand harsh weather conditions. On the flip side, the ability of mental time travel allows humans to communicate past events, summarize past experiences, and cross-generational memories. However, an individual's memory capacity is limited and eventually erased upon death. The ability to mentally time travel enables us to foresee what memories future generations might need, thereby passing down intergenerational memories and knowledge to create a collective future. In essence, mental time travel forms the cornerstone of human culture. Nevertheless, different ethnic groups and cultures have significant differences in how far they traverse into the future in their mental time travel. Anthropologists discovered the Piraha people, an indigenous tribe in the Amazon rainforest, who seemingly never worry about the future or store food, nor plan beyond a day. This differs greatly from most people's behavior. Modern humans are increasingly susceptible to short-sightedness. Financial difficulties like mounting credit card debts and inadequate post-retirement income often result from short-sighted behavior, where immediate gratification sacrifices long-term health. At the societal level, some countries' attitudes toward climate change reflect collective short-sightedness. The human brain is a product of millions of years of evolution, and human ancestors were once creatures that lived in the moment. Even today, brain evolution continues, as we learn to balance the temptations of immediate satisfaction and the benefits of delayed gratification. Studies indicate that engaging in mental time travel when making decisions can promote the choice of delayed gratification. In one study, participants had to make a series of intertemporal choices, such as taking a day off every month or taking a consolidated 12-day vacation at the end of the year. When the latter option included phrases like going to Paris for vacation, participants would psychologically imagine the future event, envisioning delightful scenes during the holiday. At this point, they were more inclined to choose delayed rewards, i.e., taking the vacation at the end of the year. Hence, mental time travel can counteract human tendencies toward short-sightedness. What enables the human brain to possess this ability of mental time travel? Mental time travel requires coordinated work among different brain regions and is a highly complex task involving the following steps: integrating past memories, using them to evoke future scenarios, understanding the differences between past and future to judge the desirability of actions, retaining imagined scenarios, and finally executing decisions and actions. The inner workings of the brain's cortex provide pathways to access past experiences, while the frontal lobe cortex flexibly manipulates these memories, envisions, and evaluates new scenarios. If the frontal lobe cortex is impaired, individuals are more inclined toward short-sightedness rather than foreseeing the future. Storing, retrieving, and reconstructing past information is a crucial aspect of engaging in mental time travel. Individuals with amnesia struggle not only to describe what they did yesterday but also to plan what they will do tomorrow. Therefore, memory is a prerequisite for mental time travel. Our memory is divided into two: semantic memory and episodic memory. Semantic memory is associated with information related to language's meaning. For instance, when learning something essential that needs to be remembered, the brain engages in semantic memory. In contrast, episodic memory relates to specific event scenes, involving a mental re-experience of that event. Your consciousness seems to visualize the ice, feels the cold, and recalls wading out of the shallow water to safety. Semantic and episodic memory together form the basis of how our minds project backward and forward on the timeline. Semantic memory provides foundational concepts, while episodic memory offers specific experiences. To conclude this journey of mental time travel today, what is the essence of time? Scholars haven't reached a consensus. One concept suggests that time is irretrievable, and only the present is real. Another concept, more widely accepted by physicists, asserts that the past, present, and future are equally tangible. Our brain is an exceptional time machine. It not only uses sophisticated neural mechanisms to judge time and create time perceptions but also allows us to undertake mental time travel, thereby creating a better future. Well, that brings us to the end of Your Brain is a Time Machine. Until next time, thank you for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with friends to combine wisdom with practice, achieve financial goals, and create a better future together. Thank you, and goodbye.